We are Grizzly, a newly founded University Rover team at WashU. We are separated into 3 divisions: mechanical, electrical, and software. These divisions oversee the chassis, science, ARM, PCB, signals, and autonomy subteams.
Over the past year, WashU's inaugural University Rover Challenge team, Grizzly, has been hard at work creating a rover that we will take to Utah this May. The mechanical subteam has 2 projects on it, one of which is the ARM, who's responsible for creating a dynamically controlled ARM capable of completing both the delivery and equipment servicing missions, and the other is Chassis, whose responsibility is creating a flexible base that is capable of going over all kinds of terrain to support our science mission as well as our ARM and our electrical team. Both teams utilize an iterative prototyping process that allows nimble design changes and takes advantage of expertise on the team in CAD, 3D printing, and traditional machining processes.
Grizzly's ARM features 5 degrees of freedom mounted on the Lazy Susan base, allowing for full 360-degree rotation. The ARM can be swapped out using 4 machine screws to allow it to easily swap with science. Rotation is achieved using a worm gear reduced go-build motor, allowed for precise and controlled movement. The shoulder and elbow joints are also powered by high-torque go-build DC motors with encoders and worm gear reductions. This allows Grizzly's ARM to lift and manipulate heavy objects with ease. Custom 3D printed housings make motor configurations easily adaptable for different joints. The wrist assembly allows for 2 critical movements: spin, rotating the claw about its symmetric axis, and tilt, adjusting the claw's angle relative to the ground. Both are powered by stepper motors. The claw utilizes a worm screw drive mechanism operated by a continuous servo. For delicate and precise tasks, a small linear actuator is attached to the end of the claw.
Grizzly uses a 4-wheel design out of brushless DC motors with tires made in-house out of TPU to maximize control, efficiency, and flexibility. The differential bar is made from HDPE, which promotes dynamic stability at the same time also promoting flexibility. Our electrical housing is detachable, which allows quick and easy access and also protects the sensitive electronics from the elements. The ARM and science systems are easily detachable, which promotes the modularity of our aluminum chassis and also allows for the easy swapping of these 2 mechanisms.
So this is the Rover science system. It uses a combination of imaging and biological tests to detect signs of life. The dirt comes up through this mechanical auger here, and then it goes down into this funnel. On the far left container, that will be used for the Burette test. So that test detects proteins. And then the far right container here, hydrogen peroxide will be pumped into that container to detect for the enzyme catalase, which is also a sign of life. Lastly, we have the cache container in the middle. So depending on which site offers the best sign of life, we will close that. And that's it.
The brain of the rover is the Jetson Orin Nano Development Board. It'll manage our control and feedback system. The Z2 is the eyes of our operation, allowing for 2D mapping for autonomous control. Our drive motors will be controlled via an integrated CAN network, while our ARM is controlled via a serial interface. Finally, the science unit has its own Raspberry Pi, which will communicate back to our base station using our onboard networking.
Wireless comms uses a 2.4 gigahertz microtik radio to broadcast private Wi-Fi over long distances. There's one radio with a large MIMO antenna connected to the base station, and each roaming radio has 2 smaller antennas connected to it to receive and send data. The base station acts as the hub, while the roaming radios act as transparent level 2 switches for the network. To connect other devices to the network, an Ethernet switch is included on the rover, which enables the Jetson and the Pi on the rover to connect to the network. The base station radio runs a DHCP server to effectively lease IPs to the devices connected to the network. And the radios are powered by 24-volt PoE along 2 of the twisted pairs, enabling efficient power delivery while keeping a 100 megabit per second link to stream video and data.
So for the main power system of the rover, we're using a 48-volt battery, 20 amps, to step down to 24 volts, 12 volts, and 5 volts to power the different servos of the rover. For our PCBs, we're using microcontrollers to distribute and control our different servos. For our next iteration, we plan to make a main power PCB, another ARM PCB to incorporate microcontrollers to control the different servos, and for the science module to create a Raspberry Pi hat that incorporates all the different microcontrollers to control the servos and the power for them.
Grizzly software system functions with a combination of both high-level and low-level software technologies. On the high level, we use robotics operating system, which consists of 3 primary technologies. Not only does this provide more accurate and precise control of the rover, it also enables live visualization to the operator. The first is WashU control, which provides real-time control of our drive system using a differential drive controller that bases its calculations on a simulated model of a robot. For the drive system, Grizzly employs 4 O-drive brushless DC motors, which it communicates via CAN bus to WashU control's hardware interface. This also gives us real-time information about the motors, which allows us to have a more thorough understanding of the drive system. While WashU control abstracts control of our rover, we need a way to navigate. For that, we use Nav2, which is a high-level navigation planner, which allows the rover to autonomously plan out paths using our Stereolab Z camera, which also includes odometry, spatial mapping, and other technologies that we use for autonomous navigation. Finally, as previously mentioned, our high-level software system uses MoveIt2 to perform advanced inverse kinematics for the robotic arm. Using this platform, arm routines are able to be visualized and planned in RViz in the command station. By pre-baking nearly every necessary possible motion plan, MoveIt2 is able to quickly generate dynamic motion plans and subsequently joint states for WashU control to send to Grizzly Comms, the low-level counterpart of our software system, which Jerry will talk about in just a second.
As Daniel mentioned, Grizzly Comms is our low-level central communication system for bidirectional serial communication between our microprocessors and microcontrollers. Written in C++, Grizzly Comms rely on Platform I/O for embedded software development, allowing for quick real-time response, robustness, as well as modularity of the software programs, especially for hardware interfacing. With Grizzly Comms, dynamic motion planning and specific arm joint states requested from the Jetson will be sent over to an Arduino Giga to handle all 6 motors on the arm, while results from motion are fed back in a similar fashion. Grizzly Comms defines all arm joints from the base plate to the claw, depending on which motor is used. A PID loop is also being implemented to ensure precise control and minimize joint state errors.
Grizzly has worked tirelessly to make a competition-ready rover. We hope to see you in Utah.